Welcome to the subject operating systems. Today's topic is clustered systems and the operating system services which are prepared and made available for clustered systems. Like many pieces of software, operating system also evolved over a span of several decades. It began with a small piece of code called resident monitor to assist many users in using the input and output devices, because every user will have to work with input output devices. Every computer is organized as set of input devices, set of output devices, at least one input, at least one output device. There is a central processing unit, there is memory, and there is control. These 5 components are very essential to make computing happen. As we think, becomes obvious that some computing is happening. The idea of computing is to mimic as much as possible how the human brain may be doing the computing. We think that this is the simplest way in which we can show that computing is happening much in a similar way as the human brain is solving computing problems or all problems that are computable. Now, in this case we adopted the architecture given by von Neumann, where the entire program must be in the main memory, there must be the shipping of data as well as the execution instructions into the CPU, back and forth, lot of shifting of the data and the instructions, executable instructions happen between the main memory and the CPU, and it goes for output. Input output devices are very slow in comparison to the central processing unit, and the necessity for doing back and forth transfer of data and instructions between the central processing unit and the main memory has created a bottleneck, and every activity in this computer organization happens whenever the clock, which is in the control unit, ticks. At every clock tick, one action can happen. Suppose we want to make this exercise faster. Obviously, we want to make things faster. We do not want to spend half an hour to get one cursor, one prompt. The machine is expected to be faster. It is true that the success of this model, von Neumann architecture and the computer model, has fueled a lot more work in this model. Input devices have become faster, output devices have become faster, the variety of input devices and output devices has grown phenomenally, the CPU has become faster, the main memory size has increased, and we talk about the clock speed. At every clock tick, if one action has to happen, if the clock is giving ticks very fast, more actions will happen, because now the devices are faster. Now the components of the computer are faster by manufacture. However, this clock is generated by a crystal oscillator which cannot oscillate beyond a particular frequency, because nature has imposed a limit. So, we started talking about phased clocks. Multiple clocks are there. In between the clock pulses generated by one clock, we will use another clock to generate pulses, and we talk about synchronous circuits where at every clock pulse one activity is defined and it works. Again, that has a limitation. We cannot hope to get more and more speed out of the single central processing unit, because at the end of the day that is also made in silica. It takes time. The electromagnetic wave takes about 1 nanosecond to traverse 1 foot of a copper wire. It takes that much time. So, there is no way in which we can come out of this von Neumann architecture. There is no real way in which we can whip up the clock. The components will have their limitations. So, a very commonsensical argument it appeared, saying that why can't we have multiple processors on the same machine? Well, technology will have to advance, we need to have better fabrication techniques. So, to make the machine perform better, towards the goal of getting better performance, while the technology to fabricate multiple processors, multi-core architectures which are now happening, these ideas were there, high performance computing ideas were there. One of the simple practical solution was to use the existing single processor computers connected together in some sense of clustered computing. It is not entirely out of fashion, but we are using clustered computing at the high end, high performance computing, because we know that the single uniprocessor machine today is much faster than what it was 5 decades back. It beats the speed of the human who is using, and we are now wishing that we become much more faster. Human beings must become much more faster. The machines have improved, the machines have become much faster. So we took to this idea of clustered computing, while the technology to fabricate and work with multiprocessors, multi-core architectures was happening. It was happening in research, it was happening in fabrication. Clustered computing was becoming very popular. What is the most famous application? We talked about a fact that there is a serious computation going. Accuracy and precision are absolute necessities in this computation. So, a cluster computing, let us say 3 computers are doing the same calculation, and if all 3 computers come up with the same answer within the margin of errors, then we say the computation is correct and we can go ahead with whatever is computed. So, one of the first and the most famous applications for clustered computing, because we are not able to make it faster, we are not able to make it take complex problems and then get a verifier that says that the outcome, the result, the output is correct in terms of precision and accuracy. We were talking about serious scientific computation where a marginal error in some decimal place, 25th or 30th decimal place, will mean a huge error. It cannot be accepted. So, one of the most well known applications for clustered computing is use 3 computers to do the same operation, and at the end of the entire exercise, when we compare the output, if the output is within the acceptable margin of errors or limits, we go ahead saying that yes, 3 computers have done a cross checking, everything is done, this is accurate, let us go ahead. For that we need to make them faster. It was true that one machine was there, it was doing whatever is the output, we were going ahead with that. Now, the cluster computing, these 3 machines will have to talk to one another at regular intervals and then say that are we all right at this stage, at this stage, at this stage. We have begun to address really complex problems where that kind of a cross checking at intermediary places is necessary, and then when we go ahead and use that computation, the result will be correct. This is how we have fielded the first set of cluster computing. It has an inbuilt check, it has an inbuilt checkpointing, it has a way of telling that at this point the computations were in concurrence. We need to have such method not only to increase the performance, but also to cross check whether we are adequately accurate, adequately precise. It is a case of $1,000,000 projects, huge projects. Some of the technologies which are very famous are Beowulf cluster, and as a construction it is used in bioinformatics, parallel computing, and at home projects. 256 process Sun cluster, it is a great cluster. We are talking about a very simple idea saying that all are there, 256 processors are there. What kind of operating system services you have? It should have a facility to check the clock, check the clocks, check the cluster, check the output, comparison. These are certain additional services, additional functionalities demanded by the cluster computing. This is how it has evolved. We started talking about time sharing, and we started talking about the way in which the single program, single user, single machine was very quickly outmoded. We wanted multi-programmed, we wanted time sharing systems, multiple users, multiple tasks, so that when the user is doing the input output, as I said earlier, the input output devices are very slow compared to the central processing unit. So, we have had time sharing, we had real time systems as 2 separate ideas. Time sharing is what we normally talk about, multi-user multitasking. Real-time systems place a demand saying that next few seconds this exercise must be done. Most of the times the real-time systems are built on multi-stakeholders, and we have to have a way of saying that we need to meet, we need to synchronize somewhere. In all these cases the cluster computing methods seem to be working. Personal desktop computers, which have become very fast, and people started using them in a manner where we did not imagine. The way they were connecting multiprocessor systems, as I said, the uniprocessor system itself has been pushed to the extreme. The simplest way of getting more speed, more performance is to talk about multiprocessor systems, but by the time they were fabricated it was taking time. Networked distributed systems, web based systems, now all these things can be used with this core idea of cluster computing, which is so necessary and so essential to prove that we can also take care of precision checking, accuracy checking, let more systems do the same work and check whether they are getting the same result or not. Batch multiprogramming does not support interaction with users. Time share, these are all the advantages. Processor's time is shared across multi-users. Not all operating systems are general purpose systems. Real-time systems are dedicated systems that need to adhere to deadlines, time constraints. How do you know whether so many processors are meeting the deadline? Cluster computing. At this point in time, this result is expected. If one fellow didn't show up, what do? Correctness of the computation depends not only on the logical result but also on the time at which the results are produced. That is the crux. Correctness now has a qualifier. It is not that you have claimed that this is the program, it is starting here, it is ending here, I can come and tell that it is correct within the estimated space, within the estimated time complexity. It is necessary that it should also happen on time. If it is not, then we are not saying there is a correct solution at which the results are produced. This is one of the reasons why in 1968 and 69 the NATO conferences have very carefully defined what is called software engineering. We need to have estimated time complexity, space complexity now gets translated. For an algorithm we were talking about time complexity, space complexity. It is now estimated that we should have time, cost and quality. All these are important. Quality is the king, and what we have been doing in software engineering, very carefully we have positioned quality as the king, and then we realized that to produce that kind of a demanding quality, we are not able to meet the estimated time and estimated cost. 200% more cost, 300% more time. Therefore, if quality is right on the top, we are claiming that our success rate is still 35 to 36% success rate, which is not called correctness in the strong engineering disciplines. It should be produced on the time, then it is correct. So this is how it was. We started with personal computers. This I have said, they are now much more faster, they can adopt. This is a typical set of components which I have described in the beginning. The personal computer components are very easy to understand. We can simply take a look at the components which are there. The monitor, the keyboard, the USB printer. This is something which facilitates the connection of input and output devices. The disk drive for the memory, keyboard, video controller, memory, CPU, some are input devices. Keyboard is an input device. We have a video controller, we have a keyboard controller, we have a USB controller, hard disk controller, there is a bus, we can have a printer here, USB for a printer, printer is an output device. So input device, output device, the CPU, monitor is an output device, printer is an output device, keyboard is an input device. So we have memory, we have so many things that are coming together. This is a typical computer organization. But what is the problem? The problem is lot of shipping of the data from the memory to the CPU, from CPU through this bus, the shared bus to the printer, getting it from the keyboard, lot of congestion. That's what is called von Neumann architecture, and von Neumann bottleneck is simply not possible to avoid. How much ever you push the clock, At the end of the day, we will be caught on this bus. It's a simple narrow road. When only one car is going, it is fine, but when 1000 cars are going, there is a problem. It gets choked. We don't know what to do about it. So much in a similar fashion, there is a von Neumann bottleneck in that architecture which we are not able to avoid. There are multiple architectures. However, the success story of personal computers was such that we were not entirely wrong in thinking that the simplest solution is to multiply the CPUs, multiprocessor systems. We are not entirely wrong in taking that decision, rather than working around saying that I will come up with a completely new architecture. Many researchers are working on different architectures. There are so many architectures that are coming, but the roaring success of a personal computer was such that it became an automatic, business wise and a pragmatic decision to say that why can't we multiply the processors? Why should we have a single processor? So, single instruction, single data, multiple instruction, multiple data, this is a multiprocessor, this is a uniprocessor. So, we can have multiple instructions working on multiple data simultaneously. This is the idea which we brought about. Multiprocessor systems are with several CPUs in close communication. It shows increased throughput, it shows economy of scale, increased reliability, graceful degradation or fault tolerance. If 5 computers are in a cluster, 3 are concurring with the result, 2 are not concurring, then we have a closed decision. If 5 are concurring, it can go ahead. We will define saying that at least 4 must concur before we say yes, the calculation is correct, the computation is correct. There in time, real time, everything is correct wherever the machines are. In theory, we have adopted the ideas from distributed systems, grid computing, cloud systems. The goal was to achieve this kind of a method by which fantastic computational resources work in tandem towards solving a problem. At every checkpointing, they cross check with one another. That is the essence of cluster computing. Lot of good ideas have gone behind cluster computing, and operating systems provides the service. This is a simple symbolism. We have a memory here, we have a multi-core now. Instead of having different multiprocessors on a single processor, we have multiple cores. One core it can process. There are so many processing elements on a single CPU chip. That is another model which is possible. From all these ideas, we have built the base for clustered systems, which is not merely high performance as a raw speed, but also an inbuilt correctness verifier, inbuilt way of cross checking, inbuilt way of making sure that close calculations will have a cross check on accuracy and precision. And then what we need to understand is these processors also have their own external memory. Communication takes place with high speed channels, provides high availability. They are all called closely coupled systems. They are very closely coupled systems. This is a way in which parallel computing began. They are all there, they are all knitted together. In theory, we tried to emulate this idea on loosely coupled systems also, but the term clustered computers, clustered computing, clustered systems usually connotes closely coupled systems. They are all together, knitted together, and the architecture is several computers are looking at a common storage network. This is a better view of the way in which we talk about managing application, parallel libraries, local OS, everything is there, and what we need to understand is that they are all equally capable nodes which are connected. Lot of processing is happening in each node. In each node, there is lot of processing that is happening independently based on its own clock, its own way of operating, and what we need to understand is at regular intervals which are preordained by the programmer, there will be a master node that will cross check. They will have to report to the master node. These ideas found their way of implementation into various distributed computing protocols, grid computing, cloud computing. We need to understand that they are closely coupled. In theory, today the networks have become very fast. It does not really matter to me where these machines are physically. So, we think that the idea is good, clustered computing idea is good, provided the operating system has adequate services to connect to the networking capabilities either at the hardware level management or OS internal APIs or system call level, or even at the language level with the OS support for with standardization. So, that is how we have been talking about, and what we need to understand is that usually sharing storage via a storage area network, we think that the real concern here is the storage area network from which the synchronization begins. All these are independently working, the data, the way they are working, they are all coming from a common storage, and we have therefore said that high performance computing is one very good application with adequate parallelization on closely coupled systems. The network systems distribute resources and computation among several physical processes. They are loosely coupled system. If they are far, its own local memory. In theory, clustered computing simply connotes a closely coupled system where shared memory is implied. Shared memory parallel processing is in itself a good study. Clustered computing natively is amenable for this kind of an implementation of parallel computing, which definitely promises much faster results, much more faster than what a uniprocessor can do. As a matter of fact, many times we used to think, we keep thinking that certain tasks in a given program can be done parallelly, but on a uniprocessor that parallelism is apparent. You can only give a proof of concept that it can be parallelized, but speed up, the advantages that we are talking about will happen only on multiprocessors, multi-core or distributed systems across the network. So, we keep talking about a network system where the network will facilitate all this. If this network is faster, whatever this network is doing as services, so an interconnected idea which is essential, which is quintessential to the implementation of clustered systems is the fact that we need a fantastic component, we need a very good component here. Whether we call the same good old routers are not adequate, they simply route. Even bridges, they are not adequate. We may need to have gateways, much faster gateways. We need to have a sophistication in this network. Today we are talking about high speed networks, plenty of research is going on. We can also talk about software defined networks. We can think of using this particular block in an effective way where whether it is closely coupled or loosely coupled, the idea of clustered systems is very valid, and operating system is now getting more and more demands to support that kind of an architecture where it does not matter where the physical machines are, they can participate in a cluster, check, cross check, precision, accuracy and everything, and then come to a conclusion that within a real time, within a given time, yes, it has been done correctly. The idea of computer clusters evolved after looking for a better way to efficiently manage the cost and availability of microprocessors, high speed networks and software. That is the essence of what I have been talking about. If these are to be used separately from each computer, it costs the company a heavy sum. Cluster systems may consist of personal computers connection, but by the correct usage and implementation of cluster architecture, high performance can be obtained. So, you can have individual personal computers connected together, that is the idea. So, to summarize, cluster systems are also known as computer clusters, refers to a group of cluster of computers working together. The task to be performed is assigned using specifically designed software. It can operate across network, it can operate across closely coupled systems. It took us quite some time to achieve this kind of a maturity in the way machines get connected and the operating system provides services. I do remember the early days of concurrent programming, parallel programming, distributed systems, grid computing, where these ideas were very conceptual. Today a lot of people have understood these ideas, however programming those systems is becoming a challenge, and therefore the utilization of clustering as an idea is limited to a very specific expert group, and we do not have that many people who are doing the programming. The advantages are obvious. We have the way of looking at high performance, large capacity, high availability, incremental growth, clustering applications, scientific computing, making movies, commercial servers. We can do the movie from anywhere. It should be possible wherever the exercise is happening. We can bring together several things and then make a single machine do all the synchronization and putting together. I do understand that you can create music in this manner, it should not be a big challenge. Cluster closely coupled in single place, see so many nodes. I said the sun has implemented 256 nodes in a cluster. This is also possible, each one is a personal computer and they are all getting connected. There is one single box here, which is the way in which those things connect across the network, one monitor. This many pieces are coming together to form a cluster. VAX cluster remains the first which we were studying in this manner. They created a very special operating system called VMS. VAX VMS was nicely adapted to VAX clusters. They have 3 machines and at least 2 machines must concur at the checkpointing of the calculation. At the checkpointing, the calculation is within the acceptable limits, marginal errors, we go to the next step, otherwise we roll back everything, start afresh. No 2 computers even from the same brand perform in a similar manner. No 2 clocks show the same time. Therefore, we need to understand very carefully that from multiple sources all these things should go into our basic architecture, high performance and correctness. That is the goal of clusters. Towards that, we are demanding more and more services from the operating system, and it is happening in a seamless manner. Today lot of capabilities are there, lot of people have understood the ideas. However, this much of programming capability is expected to develop parallel applications. We need to have a way of talking about applications, sequential applications, parallel application. On a uniprocessor, whatever parallelism you are suggesting is only apparent. We do not have the speed up, it is just a trial saying that yes, it can be parallelized. However, it is on a multiprocessor, multi-core, later on grid, distributed. These are all closely related ideas. Gradually, as the technology evolved, as the operating systems services evolved, as we progressed further, we started looking at all these ideas in a perspective where we are not merely looking at the raw increase in performance, but complexity of applications grew phenomenally. We celebrate that complexity. We talk about accuracy, we talk about precision, we talk about checkpointing, cross checking at regular intervals. So, these are all the simple disciplines in computing which is necessary. High speed network switches, as I said, today we have software defined networks. There are several applications: science computation, digital biology, aerospace, resources. Without this clustering, without all these ideas, aerospace would not have come this far. We are talking about fantastic applications in aerospace, and we have been worried about many architectures simultaneously operating, not necessarily uniform architecture, many architectures, parallel vector processor, symmetric multiprocessor, massively parallel processor, cluster of workstation, distributed shared memory. Towards inexpensive supercomputing, we need to have a cluster. Supercomputing was a fantastic idea, we can make it faster, 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 but cluster computing is no less, provided we have that programming capability. It is a choice we have. Supercomputing is so fascinating that we had Cray supercomputer, multiple clocks, that was great. Supercomputing architectures have improved vastly. Cluster computing still remains very attractive because we are already purchased simple machines. Can you put together? The network is a computer, is the idea. Towards that, we have to build operating system services. A computer cluster is a group of linked computers working together closely so that in many respects they form a single computer. But this is something which we need to look at it. Later on, we will tell that it can be spread across a high speed local area network. You can still program it, software defined networks, there is a cluster middleware, multiple CPUs are working and they are all clustered. We identify that in this exercise of computation, these many machines are bound together, and this is how we operate. We have a simple middleware layer which provides what are called multiprocessor interfaces. Several processors are coming together, the cluster classification, high availability, network. This is on high availability basis, mission critical applications. There is no downtime for that, it should be there. So, we have a Linux cluster that will operate. So, some years back we had a Linux cluster working for bioinformatics, network load balancing, science clusters. Beowulf is a very famous science cluster. A Beowulf cluster is a computer design that uses parallel processing across multiple computers to create cheap and powerful supercomputers. A Beowulf cluster in practice is usually a collection of generic computers, either stock systems or wholesale parts purchased independently and assembled together with an internal network. So, you can virtually get anything that is in conformance to the computer organization that has been described, use the operating system services, put multiple machines together and gain the performance and the power of a supercomputer. In theory it is possible, in practice it is very demanding on the programming, it is very demanding on the operating system service provider. The size of the operating system is no more a footprint, it is hogging memory. Now we said that memory is very inexpensive. Don't worry about the size of the memory, first talk about the OS services, first talk about the functionality that you want to implement. Nothing is impossible, we can push more and more to the operating system. The typical Beowulf cluster happens like this, slight animation, but then it works as a master. There are nodes, essentially it remains the same. The way we have been talking about clusters is there will be a master to which all nodes will report, and the master will cross check what is to be done. Communication layers will happen. If we want, we can see it again. It is useful to see that one after one we can add the cluster. The machines will start walking into the cluster, 1 machine, 2 machine, 3 machine, and the services are expected to factor. Initially there was only 1, now it is 2, then it is 3, then it is 4, 5, 6, 7, and master nodes are ready. Then there is a communication channel. In order for the master and node computers to communicate, some sort of message passing control structure, MPI, message passing interface, is most commonly used for such controls. We can construct it using hardware system structure, resource administration and management, distributed programming libraries and tools, parallel algorithms. Thank you.